Hi. Hi everyone, so my name is Mathieu. I'm doing a PhD in Montreal with Miguel Anjos and Andrea Lodi, who are my two supervisors. And today I want to talk to you about a project that I've been working on for the past few months that's called Tulip. It doesn't mean anything special, it's just a flower. I like that kind of flower, so it has IP for interior point. So Tulip is essentially an interior point solver that I coded. And the main feature that I want to advertise here today is the fact that it has an abstract linear algebra, and I'll come back to it afterwards. Just before I start, I'd like to get a sense of how much details I should tell you about interior point and stuff. So can you please raise your hand if you're familiar with optimization, linear programming, interior point algorithms, homogeneous self-dual embeddings? Okay, amazing. Great. So I'll try not to dive in too much into the algorithmic details, because that's something that you can find in some references. And I'll try to focus more on the Julia part and the specifics of this. All right. So first, why should we look at linear programming? Linear programming is essentially linear objective, linear constraints, and instance from non-negative variables. So that's generally how you will frame your problem, which is called a primal. And if you're familiar with LPs, you know that there's also a dual problem that I represent in red. That essentially is like some sort of an equivalent problem, but not exactly the same. And interior point methods will work on both these problems at the same time. Okay? So LP has been around for about 70 years. You can classically solve LPs with either the Simplex algorithm or an interior point method. These are the most two classical methods. There are other algorithms you can use, but I'm not going to focus on that. And LP is important because it's essentially used in a huge number of problems. So I'm personally involved with mixed integer linear programming, where you essentially solve sequences of LPs. If you've ever worked with decomposition method like Dancy-Wolf decomposition or Bender's decomposition, you alternate between solving LPs. If you're doing polyhedral auto-approximation for, say, conic optimization, you're going to solve LPs. If you're doing cut-and plane methods, probably you end up solving LPs, and so on and so forth. So it makes sense to look at LPs and to try to solve LPs fast. And this is essentially what I try to do. I take an LP, I try to solve it as fast as possible. So in a nutshell, this is your linear problem. So the feasible region is in blue, and you try to go as far as possible in the direction of the arrow. So the Simplex algorithm works by going from extreme point to extreme point. So you move. Each move is called a pivot. It's very cheap to make a pivot, but you can need a lot of pivots before you solve the problem. So this algorithm was proposed by Danzig in like the 1940s, and it's been implemented ever since. The other approach is called an interior point algorithm. So you start in the interior of the region, hence interior point, and you make a sequence of jumps. So you go from the first point to the next point, and then another one, and then another one. Each of these moves is extremely expensive compared to one iteration of the Simplex algorithm. But the nice thing is that you only need a handful of them. Typically, you're going to need 30 iterations in order to converge and solve the LP to optimality. So interior point algorithm is essentially all about how do I compute this direction here? So how do I go from my current point to the next one and to the next one and so on? And so the purpose of my talk is going to try to explain how you can compute this as effectively as possible. Okay? All right. So I'll just give you a bit of background on interior point to set up a few things about linear algebra. If you don't care about interior points, you don't have to listen too much. Just look at the colors and the plots. So this is the LP. Okay, so the optimality conditions for that, I write like this. So it's a system of equations. Basically, you have primal feasibility, first line, and dual feasibility, something weird that is called complementary slackness. That tells you that the variables times its reduced cost should always be equal to 0 at optimality. And the fact that your primal and some of the dual variables should be non-negative. And coming back to the figure that I showed you before, Essentially, primal simplex will satisfy the first three all the time and only give you a non-negative S dual variable at optimality. Whenever you end up with S non-negative in the primal simplex, you stop because you just proved optimality. Interior point methods will keep primal and dual feasibility, but will only satisfy slackness at optimality. So in fact, in practice, you don't even satisfy this at every iteration. You only get it at optimality. But that's roughly how you could think about it. So very briefly, the main paper was written in 1984 by Conor Carr. Then there's a very famous paper from 1992 that essentially gives you the basic framework that is underlying probably 90% of interior point implementations in linear programming. So that's called the predictor corrector algorithm of Merotra. And I'll make a few references about this. And in 1996, there was an algorithmic innovation that was proposed by Gonzo that is called multiple centrality corrections. If you're familiar with interior point, you might recognize some of these. If you're not, don't worry, I'm just putting your pointers if you're interested. So the reference textbook is a book of Wright. And if you want a more recent survey that also tells you a bit about algorithms and more recent development, you can look at the survey by Gonzo. As far as software can go, pretty much any LP solver should have an interior point algorithm implemented. So any commercial solver will have that usually under the designation barrier. So if you do Simplex barrier or Gurobi barrier, you're essentially doing primal dual infeasible interior points. And then open source software also has interior points implemented, such as CLP or GLPK, although CLP and GLPK do not have a very high performance interior point. CLP is mainly a simplex algorithm, and they added an interior point afterwards, but they're not the best algorithms and implementations you could find. OQPE is a solver that was written by Wright, I think in the 90s or early 2000s. That's written in C++ that aims at doing essentially what I do, but in C++ and as of 15 years ago. So I don't think it's really developed anymore. I don't know if many people use it. My understanding is that most of its code base has been integrated within the PIPS solver that does parallel interior points. And there are a couple of others like PCX and HOPDM. These ones are written in Fortran. I don't think the code is completely open source, but if you like Fortran, you can look at this. It's Fortran. All right, so in a nutshell, what does an interior point algorithm do? You compute an initial point. I'm not going to describe how, just believe me that I can compute an initial point. And then I'm going to compute a search direction. So remember the plot where I had the green dots and the arrow, that's computing the arrow. So you do that by solving a sequence of linear systems. Don't worry too much about what the right-hand side here is. Just the main point that I want to make is that this matrix and this matrix are the same. Okay, and in practice, you're going to solve a series of linear systems with always the same left-hand side matrix and potentially different right-hand sides. And that will come up later when I talk about factorizations. Once you've computed these two directions, you sum them and you make a step in this direction. Okay, so you may compute only one of them, but typically it's much more efficient to compute two. And you keep doing that until you converge. And there are people who did a lot of math to tell you that if you do that, then you will converge. And in practice, it does. So geometrically, this is what it looks like. So this is your current iterate, x. You compute a first direction that is the predictor that if you were to make a full step in this, you would go outside of the feasible region. So you have to damp the step and back it up a little bit. So this first direction, the predictor here, is also called the affine scaling direction. And then you compute the corrector that essentially tells you, you know, if you sort of like try to steer a little bit, maybe to the right or to the left or whatever in an n-dimensional space, you could actually end up here. And if you make a step towards that point, you can make a much longer step. And so you converge much faster. And so this is a basic one predictor, one corrector. but you can compute additional correctors a few extra times to try to reduce the total number of iterations. All right, so current point, you compute some directions. Each of these directions you compute by solving a linear system. And every linear system that you solve within a single iteration is always the same left-hand side matrix. So there's a lot of math that goes into telling you why you will only need a few iterations. And then there's a lot of engineering that goes into how can you compute those directions fast. And in practice, that means how can you solve a linear system fast and efficiently. So wrapping it up, if you want to solve LP, so you look at the primordial standard form like this. At each iteration, you're going to solve a bunch of those systems that I call Newton systems, with always the same left-hand side matrix, but potentially different right-hand sides. It's one of the few practical polynomial time algorithms. It was not the first, but the first one was totally impractical. And interior points are extremely efficient when you have large-scale problems for LP, and by efficient, I mean faster than Simplex algorithm typically. All right, so now I'm going to dive more into the linear algebra. So essentially looking at how we can solve that efficiently. Now, one important thing to notice is that all I need to do for my algorithm to go on is to get a solution to that system. I don't care how you solve the system as long as you give me the solution. So if you want to do a factorization of this, you can. If you're in MATLAB and you just want to use a backslash, or in Julia, you can. It's not going to be the most efficient, but it's going to work. And you can code an interior point in maybe 20 lines of code. It's going to be extremely slow, but it's going to work. If you want to make it fast, then you have to dig in this a little bit deeper. And this is what we're going to do right now. So Newton systems has this kind of structure in the matrix, okay? So if you want to accelerate your interior point algorithm, there are two things you can do. You can do math and get a better algorithm that will generally lead to a reduction in the number of iterations. And what you can also do is reduce the time per iteration. That's generally engineering and better linear algebra. So that's what I'm doing here. So you don't actually solve that system explicitly because this thing is a diagonal matrix and this thing is a diagonal matrix. So typically you substitute this delta S and you get this system that is called the augmented system. It's smaller. The only issue is that this left-hand matrix is now indefinite. So it's actually quasi-definite if you add the regularization. But typically for linear programming, you will do an extra substitution and you get the normal equations. So essentially you pivot out this diagonal block and you end up with this positive definite matrix that is here. So it's strictly positive definite if A is full row rank, which generally is assumed. If not, you can do a pre-processing to remove linearly dependent rows. So A theta A transpose, which is a matrix of the normal equations, is positive definite. If it's positive definite, you can compute a Cholesky factorization. And you can specialize that Cholesky based on the structure of A. So why would you want to compute a Cholesky besides numerical stability and others? Well, you only need to compute a factorization once. And then you can solve that system with as many right-hand sides as you want. You don't need to recompute the factorization. So at each iteration of the interior point, you're going to spend a lot of time computing this Cholesky, and then you're going to do subsequent back solves during that same iteration that are going to be very cheap, because they're just going to be some triangular substitutions. And this is where a lot of the performance of the algorithm comes from, being able to efficiently compute this Cholesky factorization. So a generic solver, general solver like CLP or GLPK, will have a general sparse linear algebra that is implemented. So A is going to be a sparse matrix, and there's a code like in GLPK, you can look at the Cholesky factorization code, and it will just compute a sparse Cholesky factorization. If you have extra information about A, so about the structure of your constraint matrix, you can use that in the Cholesky factorization to speed it up. And I argue that doing that will result in significant speed up in practice. So just to give you one example, I've been working with unit block angular matrices that arise in applications when you do density growth decomposition and then column generation. So essentially, you end up in your master problem with a constraints matrix that looks like this. You have a bunch of rows that are just ones. And then you have lower blocks that in my case were dense, but maybe sparse in the general case. And if you compute the left-hand side matrix of the normal equations, you will see that it has this bordered angular structure. And this is something you can use to accelerate Cholesky. So I'm not going to give you details about how to compute that, the Cholesky factorization of that. If you have more questions, we can talk offline or ask me after the talk. But for the purpose of time, and this is how far I will go, just trust me that you can actually exploit structure. So you can exploit structure, you can exploit data types. Like say if A only has integer coefficients or Boolean coefficients, that is something that you may want to use when computing those factorizations. So summing it up and putting it all in a Julia package. So I've coded this solver that is called Tulip. It's available online at this GitHub URL. I'm just going to list a few features that I think are the most important one. So it uses a homogeneous Selden embedding and the method of multiple corrections. The upper bounds on variables are handled explicitly, which essentially allows me to default back to the same normal equation system all the time. And the algorithm itself only uses abstract linear algebra. So A in the algorithm is always going to be an abstract matrix. And then very specialized linear algebra. So I currently have a sparse Cholesky that is just using the Julia's Cholesky that I think is calling sparse. So it's not particularly performant, but it works, which is what I wanted to have. And I also coded a specialized Cholesky for unit block angular. And this one is fast. Currently, it's only interfaced through macproc base. And I'm working, or I want to work on extending the interface to MOI and to improving numerical stability, which is very important in practice, and having a better general sparse linear algebra. So that last point is essentially trying to make the solver more efficient on general LPs so that anybody could use it out of the box and solve practical instances. So I tested it on the netlib benchmark. It's a set of small LPs. I only tested it last week, and I removed a bunch of instances that I cannot solve because I can't model them explicitly in the solver. Basically, most of the time my solver can solve them. A bunch of time it will run in numerical issues, which is expected because there is nothing in the code that currently handles that. The point that actually surprised me is that my code is faster than the CLP or GLPK interior points on instances that are supposedly hard to solve. So among the instances that I can solve, among those instances that take the longest, I am typically faster than CLP or GLPK. So I didn't write this to brag. I just want to point out that there's a potential to have a state-of-the-art interior point solver that is coded in pure Julia. And I found it pretty cool. Yeah.
Saying this comparison against the interior point.
Yeah. It's always a barrier. So barrier, no pre-solve, no crossover, single thread. And yeah, I mean, it's not that surprising because CLP and GLPK don't really have a very efficient barrier algorithm. But the simplex will be completely destroyed against CLP. And then I also tested that on some more involved instances that came from a different project of mine. There are column generation-based instances. So if you're familiar with that, I essentially solve instances with up to 30,000 subproblems. Very few linking constraints, but every linking row is very dense. And that gets you a master problem that typically has up to 30,000 non-zeros, 30 million, non-zero coefficients, about 30,000 constraints, and up to, say, 100,000 variables. And so I use the same column generation code, and I try to change the solver, say, my solver or Mosaic or Gurobi to solve the master problem. And it turns out that my code is faster overall, but I really want to look at the per iteration time, which is significantly faster than state-of-the-art commercial software. So, I mean, this is common sense. There is structure, I exploit structure, I'm faster than something that doesn't exploit structure. But the point that I want to make is that if you use even a generic interior point solver and you're able to specialize your linear algebra, which is something that you can do very easily in Julia, then it's possible to beat state-of-the-art, even commercial solvers on non-trivial instances. So this is where I am right now, and I'd like to extend this to make it more available through MY and JuMP. Obviously, I have to work on numerical stability because right now I would not advise you to use it in any practical application, and possibly extend it to quadratic programming. If you want to have a more JuMP-related talk, there are two things that interest me particularly. The first one is how you can give structure information to the solver. So I told you I'm able to exploit structure, but I need to know that structure. And if you only pass me a generic JuMP model, I'm not necessarily able to exploit that. Open question, how can you give structure information to the solver in a somehow generic way through JuMP? And the other one, because I was involved in decomposition problem generation, I'm really interested in the ability to take a problem, solve it, make some modifications like add cuts or add variables, change some tolerances, and resolve it again without having to recreate the model and so on. And do that, of course, efficiently. So if these are of interest to you, please come in and let's chat in the next few days. That's it for me. Thanks.
Any questions? Have you thought about using iterative method? How does that interact?
So I have thought about it. And that's about as far as it goes. How would it interact? If you go back here, so once I get there, so no, actually. Okay, so I lied a bit. So in my code, there's a function that says solve Newton system, and then you can plug in whatever you want. So there's a pre-processing phase at the beginning of each iteration where you will compute the factorization, or you could override that method and compute a preconditioner instead. And then you pass either this factorization or preconditioner to a specialized method that will either do a substitution or an iterative method to solve the Newton system. And then within that Newton system, I do the augmented system and normal equation substitution, and this is currently how it works. But there's nothing that would prevent you from, say, just computing a preconditioner, and then instead of going for a substitution, just do iterative methods to solve the linear system. In practice, I don't know how faster it would be. And obviously, I haven't tried it. Yeah.
The really large problem you were doing, the master problem. So you said you had like tens of millions of non-zeros. So you're doing sparse Cholesky to tens of millions of non-zeros.
No, so actually, if you have this matrix and you try to compute a sparse Cholesky of this, you can essentially pivot out all this diagonal block, and you end up computing a Cholesky of the 10th true complement that is here. And for the instances that I had to work with, this guy is probably 100 by 100 or 200 by 200. So I do a very big computation of true complement that's all dense, and then I just do a dense Cholesky that is super fast. And it works, luckily. But in general, you would want to do a sparse Cholesky on that.
Yep.
Thanks.